morning. Or actually good afternoon. Sorry I'm not there today. Molly's sick and I had to take the day off. But we're still going to continue and go ahead with continuity because this section is pretty easy to understand. We've already actually talked about a little bit of it, so it won't be totally brand new. So if you'll turn to your continuity section, we're going to start with that first box that says definition of continuity. And I apologize if we get interrupted every once in a while because Molly's still walking around. Molly, you want to say hi?
Hi.
Are you not feeling good?
Hi.
How are you guys?
Hi, guys. Hi, Coco.
I don't think JoJo's in that class. Say bye-bye.
Bye.
Say have fun learning. Oh, and she just gave you a kiss. Okay, so hopefully you found that box. There are 5 qualifications for a function being continuous. And normally if I was there, I would ask you to give me them because we've actually already talked about all of them. But the first key one is that the graph... Molly, let go. No, it is not yours. It's Mommy's. Go read your princess book. Yeah, go get your book. Okay, so the first qualification is that the graph is unbroken. Usually you can visually see that very easily, or if you know there's an asymptote or a hole in the graph, obviously that would be a discontinuous function. The second qualification is that the function at c, so whatever that c value is, that x value that you're looking at is, function at c is defined, meaning there's no hole. Now, these two are obviously tied together because if there's a hole, then the graph is broken, and then the first qualification doesn't meet. So these 5 you're going to see are very similar statements, but we have to list all 5 because they all pop up at different points in time with a function being continuous or not continuous. Okay, the limit exists as x approaches c. Meaning the right hand and left hand at c meet up at the same spot. So the limit exists. 4, the limit as x approaches c of f of x equals f of c. And all that means is that direct substitution works. You don't have to manipulate it at all. Direct substitution works right away. So that's what we're going to actually tag on here to the end. Direct substitution works. Okay. And 5, it's a smooth curve or line. So basically no craziness stuff, like the oscillating stuff that we had looked at before. Okay, that next statement, if a function is continuous everywhere except at c, so you're filling in the blanks now. So the first blank is c. Again, if a function is continuous everywhere except at c, the function has a discontinuity at c. And to spell discontinuity, that's how you spell discontinuity. And then there's 2 types of discontinuity that we need to talk about. There's called removable and non-removable, which we've actually already dealt with several. I'm going to change colors here on you. Okay, so in that next box where it says definition of discontinuity, the first one is removable discontinuity. Whoa, I can't spell. Okay. Means it's continuous at all points except 1. So what does that look like graphically? Well, graphically it would be a hole in the graph. Okay. The other thing that you need to tag on there is, and hopefully you have room, is that a removable discontinuity means the problem can be removed by factoring conjugate by common denominators, etc. So basically, if you can get rid of the issue by manipulating the function and then directly substituting, if you're looking at a limit or whatever, you have a removable discontinuity, because if you can remove the issue, Molly, no. No, you can't have that. If you can remove the issue, then it becomes a hole in the graph instead of an asymptote. Okay, so the other type of discontinuity then is non-removable. And let me... Okay, so non-removable discontinuity. Figure it out, kid. Yeah, you can get up there by yourself. Okay, non-removable discontinuity means the graph is broken. Ollie. Or there is an asymptote. Okay. Which we've seen those cases. Molly. Hey. Come on. They want to hear about calculus. They don't want to hear you say hi. Okay. So at the very bottom, where it says what you need to look for to discuss the continuity of a function, and by discuss just means you have to describe the continuity. In the first blank, is it possible to rewrite the function so it is continuous? Okay, so that first phrase there, is it possible to rewrite the function so it is continuous? If yes, so if you're able to manipulate it, if yes, then the function has removable. If no, then the function has non-removable. And where you have the word removable in the blank, oh, that was supposed to be a straight line. Whoops. Draw a little arrow underneath, in the margin of the paper, and just draw like a little curve, and then indicate a spot where there's a hole. So that's a removable type graph. Non-removable, draw another little arrow, and then I usually just draw like a piecewise. Okay, so that would be an example of a non-removable graph. Alright, moving on. And we'll change colors here. Okay. Example 1 has two graphs. I want you to take a minute, and in the first graph, I want you to graph the function x squared minus 1 over x plus 1. Okay, so take a minute to graph that, and then you might as well graph this function as well. Not that you can tell what that says.